number of people here who are listed. But before I do so, I'd like to thank Claudio Zanoni, who has rescued me from this fate that everyone dreads and happened to me for the first time. None of the fonts were recognizable when I plugged my memory stick in. Claudio has miraculously solved the problem. I don't know how, and I'm extremely grateful to him. So instead of talking about no liquid crystal motors, I hope to at least talk about two. So let me proceed without further ado. I want to talk about a pneumatic motor, which was work done with Peter Palfy and Tom Hiscock, a student. Then about a Smectic C-Star motor, which is work that I started with Milos Knezovic, who's at the back there, and Martin Chopic has joined recently, and it's been, he will take this work forward in a way I'll show you. And then I won't have time, I think, to talk about a mechanical engine, which is a sort of mechanical turbine, a light-operated mechanical turbine. So that's maybe for a different day. And I would like to thank, above all, Daniel Corbett, because this work rests very heavily upon nonlinear light absorption and on the mechanics of dielectric and classical elastomers. And that is work that I have done over the years with Daniel Corbett, who's a really clever fellow, and you'll see as it goes on how clever. So this is the first motor I want to talk about, and it's a very simple idea. What one has is a battery here, V1, and it's connected via this diode to a capacitor C, which is variable, hence this arrow, and it's also connected then to a higher voltage battery via a diode. So charge can't flow back there, and it can't flow back there. And the idea is that you could send light or heat into this capacitor and change or reduce the capacitance. So it goes from some value C1 initially when it's coupled here to a final value C2 when it will be coupled to this thing. And so, oh, the fonts work perfectly, beautiful. So the initial charge, Q1 on this capacitor, is just its initial capacitance times the voltage across it. And as we decrease to some intermediate value CB, which is between C2 and C1, then actually the voltage rises as I reduce the capacitance at constant charge. So it's a very simple idea. If you reduce the capacitance at constant charge, the voltage has to rise. And it's at constant charge because the charge can't flow backwards through this diode. And then I further decrease the variable capacitance from CB, this intermediate value, to C2. And as I do so, the voltage would like to rise above V2, but it can, the charge instead flows through here and is stored in the battery at the higher value. So there's a new value of Q2, which is C2 times V2 in the final state, which is less than the original charge on the capacitor. And the work done is the charge transfer. It was originally Q1 and is finally Q2 on here, so the difference has been transferred from the voltage V1 to the voltage V2. And then finally we turn the light off, and the capacitance rises again, and ultimately it will rise back to C1, and the charge will flow back on, and this Q1 on it again, and it's at voltage V1. And then we can repeat that cyclically, and we have pumped charge from the low battery to the high. Now you might argue it would be not so good to take charge out of this battery V1 the whole time and put it into V2, because you'll exhaust the first battery. And of course you've still gained energy, but it wouldn't be very practical. And on a good day, and today is not a good day, I could understand this circuit. It was given to me by one of my compatriots in New Zealand who works on dielectric elastomers, and it's very clever. You use this battery to put the charge on here the first time, and then you start cycling this through its cycle, and the voltage rises in the way I've described, and then you turn the light off and charge flows back in, but this time not from this battery, but actually back through this sequence of conductors. It's miraculous, and on a good day I can understand it, but I can't at the moment, I must confess, but I have a handout of this, and people who can understand it can explain it to me afterwards. And I can see somebody nodding who obviously understands it perfectly well, so he can tell me. Anyhow, I've seen this in action. The voltage rises pretty well without limit, and the research students put on heavy leather rubber gloves and then attend to the dielectric elastomers that are driven by this sort of system. So it is real. Okay, so let me summarize now this idealized form without this tricky circuit in it. I start at A, state A, which is V1, Q1, and the original capacitance, and this is going to be a pneumatic now, so I'm calling this original large capacitance in C1, it's actually Cn for pneumatic. And I heat this, and initially it's at constant charge, you recall, because there's a constant charge on here while this voltage is, the charge is flowing through here, the voltage is rising, the charge has flowed through here. As the voltage rises, it can't flow back, and it can't yet flow forwards. So we're on this branch here of constant Q. We get to this intermediate state where the voltage has risen to the final voltage V2. At this point, the voltage is constant and the charge is flowing out of it. The temperature now has reached the isotropic state, and then I start cooling down. I go back to some intermediate state where the voltage is dropped to V1, and then it replenishes with charge back to Q1. So that's the cycle. Where I say heating or cooling, it could equally be illumination or darkness. And the capacitance ratio is very important. It's the ratio of this value of the capacitance to this value here, and I call that xi. So we can optimize the output. You recall the output was the charge transferred times the voltage difference, and I can calculate the charge transfer, and I get this expression here, and I optimize that over the choice of intermediate capacitance where the voltage has risen from V1 to V2 at constant charge. And the optimal one is this value here. And because I can write Cn V1 is equal to Cb V2, I can put Cb into here and solve for the ratio of the voltages, which is equal to 1 plus, half of 1 plus the ratio of the capacitances. So I can stick that back into this expression for the work, and this is the optimal work. The factor of quarter there, which is always a bit of a curse. It depends on the initial capacitance, the initial voltage, and this capacitance ratio. So to make this a good motor, I want to have a large initial voltage, and I want a large capacitance ratio. So we can look at the working material, which is one we're very familiar with. It's a pneumatic, and a pneumatic liquid crystal has this discontinuous Q against T curve where there's a jump at the transition. And if I apply an external field, then I get these Q against T curves which no longer go to zero because of the external field, and there's an ever smaller jump till I get to the critical point, and then I have a supercritical curve corresponding to a field greater than the critical field. So I can form a cycle based on these, where I start at the point A, which is here. I increase the voltage and therefore the field as I change the temperature. So I increase the temperature and I go to another constant, eventually reach another constant field curve at the state B. Then I go down this constant field curve, field F2, and then I have a small jump left, so I'm presumably on this green curve or whatever, go up to the state C, and then I come backwards in this way here, regaining my initial, the initial fixed field curve, which goes from here up to the state A. So when I talk about driving this thing optically, then what I mean is that I take a pneumatic liquid crystal and I have some dye-like guests in it, and these dye-like guests, or these dye guests can bend if they absorb a photon, and the guests destroy the pneumatic order of their hosts. And then in the dark, or with light of a different color, I can get these back to their rod-like state and the order is restored. So that corresponds to this optical cycle, or if it was just thermal, I would have a disordered state here with no bent rods. And at the core of these things are the are the azobenzene units, which bend when they absorb a photon. They photoisomerize. So the performance of this motor would be determined by, first of all, the field, and the field should be large. Now here's a very crude estimate of what the field should be. There's the electrical stored energy, and I want to compare that with the thermal energy characteristic of the pneumatic isotropic transition temperature times the number density of rods n. Now that's a rather crude estimate. For instance, this quantity is 4 times the latent heat. And the latent heat is what I need to go from the pneumatic to the isotropic state. So it's presumably an overestimate. But nevertheless, I get a value here for the electric field which is quite high. And you wouldn't want to apply that for a long time to a liquid, a DC field like that to a liquid. So the way around that is, of course, to go to elastomers, which can sustain large fields. And I'll talk more about elastomers in a moment. The dielectric anisotropy, well, here's a value from the literature. We have 16 along the director and 4 perpendicular to the director. So you can say the isotropic state would have a dielectric constant of about 8. That's 2 of these plus that divided by 3. And so that the capacitance ratio will be the ratio of these dielectric constants, which is 2. So there's a characteristic value for this all-important capacitance ratio.
Those dyes, yes, are they also pneumatic?
Typically they are. So if you just had a pure dye system, it would be a nice pneumatic. But you don't want it pure, you just want a few guests there. For reasons I'll go into at the end. Right, so another problem is the photon energies, well, they depend on the dye color. And ideally you'd want to use a mixture of dyes so that if you have the solar input, you absorb from all parts of the solar spectrum. But if I take an average photon energy, it might be 2 electron volts, and that's a huge thermal energy of the order of 60 times kBT, where T is TNI. So you're really putting in far too much energy for the system. On the other hand, you only want about 2% of the rods to be photorods and to absorb. They can already destroy the pneumatic order when there's 2% of them are bent. We know that from either photon counting, where you see how quickly the pneumatic state is lost, or from the addition of bent molecules that, that destroy the pneumatic order when you put maybe 2 or 3% in. It's equivalent to a heat-induced effect, but one has to be careful about the Carnot efficiencies, the second law, because the reservoir temperature you might consider is very high of this order. So the efficiency might also be rather higher. The surplus heat from actually these very energetic photons causing bend also suppresses the order. So they add to the optical effect and increase the efficiency beyond what I'm about to show you. Right, so let me now take an elastomer because we want to avoid this conduction problem. They don't flow, which is good, so you don't have an electrohydrodynamic instability, and they don't allow ions to travel very well, so they impede conduction. They're known to operate well at 10 to the 8 volts per meter. And moreover, if you look at the performance of dielectric elastomers as actuators, then actually their output is enormously enhanced if you pre-stretch in one direction. And if there's time, I'll give you an intuitive feeling for why that is so. So here we take our system before with the 2 batteries connected to the electrodes with diodes, but it's a slab of elastomer, and it's got the director and the plane, and when we go to the isotropic state, it will contract that way, so it gets fatter at constant volume, and therefore reduces the capacitance. The area becomes less, and therefore the capacitance also reduces. And the dielectric constant in this direction should become lower as well. For that we need an oblate symmetry to the dielectric tensor. So that would be the idea, and then I must think about the free energy of the system. Now the free energy is, roughly speaking, well, you can prove that it decouples like this, a pneumatic free energy. the energy of the elastomer, which depends on its deformations lambda and also the order parameter, and then this electrical free energy that we looked at in the first part of this problem. So this is the capacitance, a function of the order parameter and the shape, and it's divided by the volume, which is a constant, to get this in energy per unit volume to match the others. Now the pneumatic energy is much larger than the rubber elastic energy, because the pneumatic energy has a scale which is roughly speaking kBt Ni per molecule, whereas this has an energy scale which is kBt times the number of strands. And there can be as many as, say, 50 or 100 molecules per strand. So this energy is a much smaller one. So the strategy would be to optimize the pneumatic energy by optimizing the order parameter, and then putting that order parameter into this part of the problem as a driving force. That's the first approximation. You can solve the whole thing together if you want to. And so if I look at the pneumatic elastic energy plus the electric energy, it's just this part here. I've written that simply as F now, and this is sitting in the background. So the pneumatic elastomer energy is the ratio of the shape anisotropy, or the shape in the perpendicular direction in the original state, divided by the value in the current state, and this is the one parallel to the director originally divided by the one in the current state. And I call these ratios for ease of writing P perpendicular for this ratio and P parallel for that. And it multiplies the square of the stretches, and I'm going to take the dimension to be 1 in the initial state and lambda along this slab normal in the deformed state, in the isotropic state. So this is the lambda whenever I write lambda simply, and so this is the stretch in the perpendicular direction along the perpendicular to the director along the slab normal. This is perpendicular to the director and in plane, and this is along the director in the direction z. And the capacitance gets smaller when lambda is larger, because this thickness d0 gets larger. So I've put that in there, and the relevant dielectric constant is the one perpendicular to the director for this capacitance. So if I took free energy of this form, there's a natural scale to how much the elastomer wants to deform, which is given by the spontaneous deformation, which is the cube root of this coefficient divided by this coefficient. And here's a picture of a pneumatic elastomer having these ratios varied by hot air blowing up and down a measuring cylinder, and this one has a lambda of 3, so this is the cube root of about 30 or so. So these numbers can actually be quite large, these coefficients. And the characteristic voltage, you could say, if I take out a mu, which is the energy scale, then I have to divide by a mu here underneath this voltage squared, and that combination is a characteristic voltage, characteristic of the material. And you might say it's really a characteristic field, because I should divide this voltage by this length. Right, so here are 3 choices we could have for the motor. We could have a slab with the director this way, or a slab with a director that way, or we could have a slab with a director that way and a pre-stretch across here, which is a bit problematical because we might induce that director to rotate if we were not careful. Right, so now I can work out the free energy. I'm going to deal with this pre-stretch one because it's much more efficient. And I can work out the free energy in the state with V1 applied. That's before I do any heating or cooling. If I do that, then these numbers here, the P perpendicular and P parallel, are both 1 because nothing has changed. So the free energy looks very simple, and I'm using this reduced voltage here, V, which is the square of the current voltage divided by this characteristic voltage squared times the current dielectric constant. Now, if I take a sheet of elastomer and put a battery across it, then the energy, charge pours in. There's a Maxwell stress because there's a positive charge and a negative charge. They attract each other. The closer they get under this attraction, the higher the capacitance, the more charge will flow in from the battery, and I can have a runaway, a pinch, and what's called a pull-in stability. So I have to be careful that I don't put a too high voltage across it because it will just blow up. And that's how these things typically fail. And the other thing is that if I pour more and more charge in, then actually this stretch here that I've imposed will become shorter than the new desired flattened out dimension, and the system will wrinkle. So I want to avoid wrinkling instability as well. And then when I take the system and heat it or illuminate it, then these factors P perpendicular and P parallel are no longer 1, and I have this more complicated looking expression, and the voltages change from V1 to V2, and so in terms of this parameter little v, I have the ratio of V2 squared to V1 squared, and the ratio of the dielectric constants. So what I want to do is I want to know what the capacitance is in the two states, because that tells me what the efficiency of the engine. So what I need to have is the value of the thickness, lambda, in the state A, so I minimize F1, and in the state C, where I minimize F2. So I have to do those two calculations. So I am going to take my output to be an optimal output. So, I will take the ratio of V2 to V1 to be 1/2 the ratio of the capacitances plus 1. Now this is a tricky formula because actually the voltages I get, the capacitance ratio depends on how much I squeeze the sheet of rubber, and the amount I squeeze the sheet of rubber will depend on V1 and V2. So that's not a straightforward relationship to evaluate. But basically the ratio is then the ratio of the inverse ratio of the thicknesses and the ratio of the dielectric constants. So I can put some numbers in for this. I'll take a pre-stretch of 50%, thickness of 50 microns, a modulus of 10 to the 6 joules per meter cubed, a couple of voltages here that are good working voltages, the latent heat for a typical liquid crystal, and I can, this is the expression for the work done in a cycle. This is the amount of heat equivalent I'd have to put in to have the change from the pneumatic to the isotropic state, and this ratio is 5%. Now I can refine this estimate by looking more closely at the cost of making it isotropic, by taking different sorts of dyes perhaps that have a more profound effect on breaking up the order, but the result would appear to be of this, in this range. I can extend it somewhat by increasing the pre-stretch, since 50% is not a wildly high one, and so it remains something to investigate. Now let me move on quickly to the second motor, which is a photoferroelectric optical to electric conversion. So I'm going to take a ferroelectric material, and it's going to be photosensitive, this ferroelectric material, and this is a liquid crystal work program, and you can imagine the one that I will choose. But as yet it's completely general. Now if I'm in the low temperature phase or the dark phase such that there's a polarization in the working material here, then charge will flow onto these plates to compensate the charges, the polarization charges that are set up. I then send some heat or light in, and I reduce the natural spontaneous polarization, and I now find that the compensating charges actually don't have anything to compensate, and therefore their potential must rise, and it's exactly the same as before. The potential rises, and eventually I'll transport that compensating charge out of the device and into this battery. So again, a cycle just like the previous one. So here's a cartoon of the setup, this is the the ferroelectric. It's got a spontaneous polarization P sub S, and I'll say 0 here, meaning at the original temperature or in the dark. There's a sheet of polarization charge here, sigma pole, associated with div P at the end of the ferroelectric. And from the sheet of charge, plus here and minus here, I have a depolarizing or a compensating, not a compensating, a field E sub S 0, which goes in this direction, opposite to P sub S 0. That means that I have quite a large potential between the top and the bottom, because it's the magnitude of this field times the distance that I've gone, which is L. And so if I want the potential to be, let us say, 0, I should have some free charges flowing onto these sheets, which exactly compensate these polarization charges, in which case I'll have an oppositely directed field, E sub F, for free, meaning free charges, and these two electric fields will cancel, and the potential of the plates will be the same. But I don't want the potential of the plates to be the same. I'd like it to be some initial value, V1, shall we say. So I then must consider V1 to be the integral of the electric field E sub F from here to here, minus the integral of the field E sub S 0 over the same distance. It's oppositely directed. Now let me look rather more carefully at this sheet. There's the the ferroelectric material here, and then there's a tiny insulating layer of thickness B at the top. So if I integrate E sub F, it goes from the top sheet right to the bottom sheet, crossing these insulation layers of thickness B. So I have to say that the field is sigma sub F divided by epsilon naught epsilon 1, but then multiplied by the thickness 2b through here and through here. And then there's it has the value, the free field has the value sigma F divided by epsilon naught epsilon, where epsilon's the dielectric constant in here, times the distance L. And then I must take off the polarization field, which goes over a simple distance L here. So that's my expression for the potential now, and it's somewhat complicated. And these layers will turn out to be quite important in a moment. So now we come back to the engine. The engine says, I'll change the polarization, perhaps being a function of depth due to illumination or heat. Then I will change the polarization field E sub S. It's now no longer E sub S 0, and it's equal to minus the local polarization, which is a function of depth and time, divided by the dielectric constants. So now I must return to this integral to get the potential. The potential will change, and I integrate this term. It's no longer a constant through the distance through the thickness L, and that's this bit here. And this bit is as before. It's this first term here of the compensating charges, sigma F. Now, this is where the diodes come in. We start off with a voltage V1 appropriate to this battery here, so that these, I have V1 is equal to this bit here minus the uniform polarization. So these are compensating each other largely. So I can write this bit in terms of the initial voltage plus this bit here, taking that over the other side. So if I put that in, I get that the on voltage after I've turned on the light is V1 plus L time divided by the dielectric constants times the original polarization minus the mean polarization. I'm replacing this integral by L times this symbol, which is just the mean. Right, so that the voltage has risen from this initial value to the on value by this amount, and clearly the voltage rise will be largest if I've switched the polarization off entirely, because it's then just given by this value here. Right, so now how much charge have we pumped, and what is the work done when we do it? We've taken the charge out at V2 rather than allowing the potential to rise to its full value. It'll turn out that this is about 350 volts or whatever, and we want to take it out at a value V2, which is the optimal. So it'll be some smaller value that I'll calculate. So the charge transfer is actually as soon as this on voltage starts exceeding the V2 of the battery on this side, we'll start pumping the charge out. So it never rises to V on, but it gives us a measure of the charge that it would have been. So it's C times the on voltage minus the amount of charge that's left at the end, which is C times V2. And C is the capacitance of the slab. And the work done is the charge transferred times the voltage it's been transferred through, which was from the start where it flowed on to the voltage where it flowed off. And I can put in the values that I had before of V on and so on for the charge transfer, and I get that the work is the difference in the voltage times essentially V on minus or something related to V on minus the difference in voltage. So it goes as plus delta V and minus delta V squared, and I can optimize that. The optimal voltage difference is equal, it turns out, to this, which is V on minus V1 over 2. So I can work out what the optimal output voltage is. It's the mean of V1 and V on. And the maximal work, putting this back into the work formula, is just the volume of the working material, the area times its thickness, divided by this factor of 4, which comes from the optimization, and the square of the change of the polarization. And clearly it would be best if I could eliminate the polarization altogether. And I'll say it a bit in a moment as to how well we can do that. Right, so I'm going to use a smectic C-star elastomer as the working a smectic C-star liquid as its working material. It will need to be an elastomer in practice. So here's the C-star elastomer. This is the layer normal. There's a tilt through an angle theta for the director. The polarization is proportional to n cross k. So n cross k, you see it's a polarization pointing this way. And this is the full result of Pekin and collaborators. And the order, the tilt in particular, will be reduced by guests which bend on absorbing a photon. We want the polarization to go across here, so we assemble this in the bookshelf geometry so that the layer normal is this way, the tilt is out in this direction n in the plane of the slab, and the polarization is in this direction, between the top and the bottom plate, as I had in the cartoon. Now, it was pointed out by Martin Choppage and others that actually this is not the ideal situation because of this problem we had right back at the beginning, that the potential is dropped also through these insulating layers. And it's not compensating there because there's no polarization field in the insulating layers, just the compensation field. So there's a high electric field energy density in these compensating layers here, and it actually makes sense to take the polarization and just put it in the plane, and then you get around that problem. Unless you apply a voltage across the system to undo this effect. And the voltage you have to put across turns out to be this voltage. Well, VC is proportional to the thickness B and the spontaneous polarization. So it'd be wise to look at the numbers to see whether this is an unfeasibly large voltage you've got to use. And it turns out for reasonable numbers that we're interested in, this is the dielectric constant of this layer, epsilon 1, that this voltage is about 1.25 volts. So it's not a big voltage, and we will always work with a voltage across here, so it would always be above this value. It turns out for these numbers, V on is about 300 volts, and therefore the optimal voltage, which is a half V1 plus V on, is about 150 volts. So that's the voltage we should take the energy out of this cycle at. And the efficiency, well, the efficiency was this work that we put in, which was proportional to the square of the change of polarization. And now I'm assuming that there's no polarization left after we've turned the light on, so this term is gone. And I'm dividing that by this work, by the work that I'm putting in, which is the energy per dye molecule in the form of a photon that I put in, times the number density of dye molecules. Remember, that was about 2% of the total density of molecules. There's about 2% of guests. And if I do that, then for UV photons, I'm thinking of 360 nanometers for azobenzene, then you have these enormously energetic photons, and the efficiency is only about 2% in the UV. Now, if you take photons also from the other parts of the spectrum, say from the red, then you multiply this number by 2 or 3, and moreover, you would want to use a broad band of dyes so that actually you pick up photons from right across the solar spectrum. And that should raise that figure somewhat. It would also be raised by having larger polarization symmetric C stars. This is already a reasonably high value, but there are values of 1,000 quoted in the literature. So, let me now talk about problems and some of the fundamental physics questions that get raised, which is how we came into this. We were interested in the underlying processes. You clearly have to use high fields, and so you might want to use elastomers. The fields are not so high. There was 150 volts across 50 microns, which is 3 times 10 to the 6 volts per meter. It's not the 10 to the 8 that we had for the pneumatic engine. The illumination changes the number of absorbers. You have to have the number of absorbers changing, otherwise you don't actually affect the state of the object. You want to change the polarization by having bent rods. The bent rods no longer absorb, and therefore you have a problem that the absorption must be non-linear. It's non-Beer because you're changing the number of absorbers participating as you turn the light on. So I want to examine that. We're changing the order by presumably the tilt angle and the coupling constant, the two possibilities. So one might want to know what a model of the order reduction is by irradiation. And then returning to this question of non-Beer, if it's non-Beer, then you have a depth dependence which is non-trivial. And because it's non-Beer, you're changing the population, there has to be a dynamics associated with it, which there isn't for Beer absorption. So there's a time dependence of this polarization as well as a depth dependence. I want to look at those briefly in the remaining few minutes. So the crudest model one can think of perhaps for this is that imagine we take a symmetric C and it's got some generalized coordinates psi that I'm not very precise about. Then the probability of that coordinate will be e to the minus the energy associated with it divided by kBt. And I'm going to say that the energy is some function of psi and multiplied by a coupling constant j. And this coupling constant j, I'm going to further say, is the dark state coupling constant j naught, and then it's reduced by the number fraction of neighbors that are not bent. So the bent ones are the cis, and this is the number fraction of cis. So when I switch this on, this number reduces from 1. And I'm going to say that the fraction of photoactive molecules is somewhere around 2%, and then this fraction, NC, of those dimolecules are going to be actually in the bent state, and therefore reduce this number from 1. So it's this fraction here which is diluting or diminishing the coupling constant. I call it a form of dilution. It's like there are fewer mesogens around the mesogen that we're concentrating on because we change them optically. Now I can put this J back in here, and I have then a J naught on the top, and this factor here, which I'll try and absorb into the T. And I can say that the T is shifted, in effect, by the creation of bent dimolecules. So there's an effective temperature shift. If I cause some molecules to bend, it's equivalent to increasing the temperature. So dilution is like increasing the temperature of the system. So here's some data from Gieselmann, and here is the polarization as a function of temperature in the dark. And then if he turns the light on, then these black squares or circles are the are the illuminated variation of polarization with temperature. And if what I'm saying is correct, then actually this one should just be a shifted version of that one, and it's not. And I'll return to why it's not. But there are some interesting things here. If I'm close to the transition and turn the light on, then I'm seemingly capable of creating enough bent rods to destroy the order entirely. So at this constant temperature up here, I can drop to 0 polarization. Whereas if I'm down here and the state is much more robust, then I cause some rods to bend, the polarization only drops this much. So how effective this is will depend on how close to the transition temperature you are. Now let me talk a bit about nonlinear absorption. If we have a beam entering this medium, then it's attenuated, I is the intensity of the beam, it's attenuated by an amount proportional to its intensity itself, times the number fraction of trans, because they do the absorption, times an absorption or rate coefficient for absorption, and then since we're looking at the change of intensity or energy, if you like, this is the amount of energy taken out from each absorption, h bar omega, times the absolute number density of dimolecules. This is only a number fraction. The number fraction of trans plus the number fraction of cis is equal to 1. It'll be convenient to take the strength of the beam and divide it by the strength of the incident beam at the front surface, and then I have this number here, which starts at 1 and can only get smaller. So I can rewrite this equation here as d curly I by dx is equal to minus nt, the number fraction of transabsorbers, divided by the Beer length, which is a length I construct from these constants here, times the intensity I. And so when I switch the light on, I haven't yet depleted the population. So, or if the light is very weak, I don't deplete the population. Then this n disappears. It's equal to 1, and it doesn't depend on I, and therefore this is a simple linear equation, and I get Beer absorption. Now the trans population is diminished by these absorptions, so that I, again with this absorption rate coefficient, I absorb photons out of the beam, and the effect of the photon's absorption is to diminish the trans population. And when I absorb a photon, there's a quantum efficiency for either going into the cis state or falling back to the trans state. So this is the quantum efficiency eta. And then once I form them into the cis state, they can relax back in a time tau, so that the rate that they go back is 1 upon tau, which is what I've multiplied the cis population by, and these cis decays tend to increase the trans population. So those are the two terms in the population rate equation. So now, if I want to first of all look at the static state, the equilibrium state, I solve this equation here where dNt by dt is equal to 0, and that admits of a simple solution. It's just, this is 1 minus nt, so I lump the nt's together, and I get nt is 1 over 1 plus alpha I. And alpha is this combination here of the forward rate and the ratio of the forward rate to the back rate, 1 upon tau. So they come together like this. And this combination is a material constant, which I call IT, or 1 upon IT, and that divides into the incident intensity. So this alpha is a measure of how strong the incident beam is. And so I can take this trans-equilibrium as a function of x and put it back into this equation, and I get an equation for I, which is now no longer the linear one, because nt goes like 1 over 1 plus I, which has to fit in here. So I can solve that equation easily enough. I can integrate it up, and I get this connection between the intensity and the depth. And this is what the answer looks like. I warned you that at t equals 0, then we have beer, because we haven't depleted the number of absorbers. And at long times, the equilibrium, so I've taken time of 5 here, think of this as the equilibrium curve, the intensity doesn't fall exponentially, it falls linearly until it's quite small, and then it's exponential just at the end. So we've got very deep penetration into the body from this nonlinear absorption, non-beer. And from the intensity profile, if I know the intensity profile, I, which I've just solved for, I can put it back into the expression for the population, and I know then the population. And so the cis concentration is simply equal to alpha I over 1 plus alpha I. And it's a cis concentration that I need to work out the polarization. The polarization, you recall, corresponds to a shifted temperature, which is T over 1 minus the cis concentration times 2%. So I take this polarization, and my job is to integrate it through the thickness to get the mean polarization. So I have to integrate the cis population as a function of depth that I know from the nonlinear absorption. And going back to the previous problem, this black line here is what I get for the polarization under illumination from transforming, or this convolution, if you like, from the dark state data to the light state. And it doesn't quite match this curve, but it's quite close. Now, I'll go into dynamics in a moment. These experiments were very hard to model because the people doing them had not recorded what the details of the absorption were. They in fact assumed that there was a uniform polarization right through the thickness, and therefore, of course, they couldn't get any sensible temperature shift. But this seems actually to work reasonably well. It would work a lot better, I think, if we knew what, for instance, the beer length was and how to scale to get the appropriate alpha. And that, I think, involves doing experiments again where these things are actually recorded as well as the polarization data. So I'd like to conclude briefly by talking about the dynamics. You see, this concentration of cis, which is causing the polarization to change as a function of depth, is also a function of time, because this bleaching wave penetrates quite slowly through the material, where I go from the initial beer state to the equilibrium, deeply penetrating state. And that will have an effect on this integral, profound effect, and it will make the engine much more efficient, because I will have eliminated the polarization in a much greater volume of the sample. So you recall the attenuation equation in its reduced form was this, and the dynamics equation, I've taken the tau over the other side, and I've reduced by I. It started off as this equation. This is the one that you've seen, and I've simply divided by I naught to make this one of these reduced intensities, and I've grouped terms together. Now these are a pair of coupled nonlinear partial differential equations, and Daniel Corbett saw immediately that you could reduce that to a single quadrature, and this is the result. Using a variable a is equal to minus log I. So a is called the absorption in chemistry. It's minus the log of the fractional change of the intensity as the light beam goes through to the other side. So, for instance, if I had beer, then I is e to the minus x over dB, and therefore, taking logs, I just have the absorption as x over dB. That's the beer absorption. That pertains at zero time, for instance. And what I have in general is a wave of penetration here, which is of I, the new profile, which is e to the minus a of x and t. And this a is the result of this quadrature here. Right. So I can now go back and say what the dynamics of the polarization change will be, because I'll put the dynamical value of n sub c at x and t into here. And doing that, I then integrate this thing, and then I have the measured polarization as if it were uniform. It's actually an average value. And I find that as I switch the light on, its value decays until it reaches the photostationary state. And this decay is a result of this bleaching wave affecting the polarization at varying depths. And then when I switch the light off, then I have a simple exponential recovery of the trans population, which means a simple exponential diminishment of this one, the cis population, and I can either calculate that exactly which of these dots, or I can approximate it in various ways by expanding this and having a single exponential for the first expansion term and a bi-exponential for the, or a square of an exponential for the second term, and so on. And I find that with two exponentials, I get quite a close match there. And you might say, well, why am I interested in doing that? Why not just take the full result that we know? And the reason is that the recovery is experimentally seen to be close to exponential, except where you're near the transition point. And that gives us confidence that actually in the other direction we can expand this when we're looking at the decay of the polarization rather than its recovery. And this is the subject of experimental investigations at the moment, and they're absolutely vital, these considerations, for calculating the efficiency of the corresponding engine. The reason for that is that if you take a layer of a given thickness, you want to see, you want to illuminate or transform a useful volume of that. How long that takes depends on how long the bleaching wave takes to get through, and you can start having back reactions before all the forward reactions are finished, and there you start wasting energy. So you want to tailor the thickness of the layer to the incident intensity and the dynamics which are being revealed by this. So these are fundamental questions still to be solved. So let me summarize. I've given you two simple ideas for a motor. The efficiencies in the UV are not high, but there's a capacity to make it broadband and higher efficiency. And there's an additional effect from the waste heat, which also diminishes the order. In the underlying physics, one might want more sophisticated models for the shift of the pneumatic and smectic order resulting from illumination. The role of non-uniformity of absorption, i.e. non-Beer absorption, is vital and quite complex. And the role of depth and time for determining the optimal cycle is important, I've just spoken about. The fundamentals of the polarization dynamics have not been explored experimentally, and much of this theory still requires testing. What are the efficiencies of such engines? And are they simply given by Carnot's law? And in the elastomers, which are clearly good for dealing with high fields, what complications are there? For instance, if we have layer shrinkage as we go from the A to the C phase, either optically or thermally, one might expect chevrons to form. What effect do those chevrons have in a solid? And that's a relevant question to ask. And I think with that, I'm done. Thank you.
Thank you, Mark, for your talk, and I would invite questions now.
Christian first.
Yeah. Okay. So when you apply relatively high electric fields, let's say to symmetric C, which is ferroelectric, then you also induce a comparable polarization, right, which is not there without the field, so which is proportional to the field. And then there are two terms in the electrostatic energy of the system. One is linear in the field, right, when field just couples to more or less constant polarization. And another is quadratic.
Yes.
Does it play any role at all?
Well, I haven't.
This mechanism, or it is not important?
Well, I hadn't really considered it, and I think the first remark would be to say one should exhaust that possibility. It could be very important. I was sort of eliminating it because I was assuming that when the guests are there, I've switched off the symmetric C star phase, but of course it's still in effect a symmetric A star, and I can still induce polarization.
In particular around the transition point. So if you want to operate around susceptibility, has a huge peak there.
I think this would be very undesirable in the sense, I mean, it may be there, but it's not desirable from the effect of these, because you want to reduce the polarization so that the compensating charges rise to their maximum potential. So I think that's probably an additional limitation of these motors, the effect that you identified.
I have basically the same.
Ah.
Too simple, but maybe I didn't understand completely. So in the second part, you are assuming implicitly that the medium is perfectly transparent, so that the propagation inside is basically due only, or the non-propagation only to the absorption by the transform of the azobenzene.
Yes.
But in reality, if you irradiate around 360, probably the medium is not perfectly transparent, and wouldn't that limit anyway the penetration depth?
Well, I certainly have neglected.
You only have one mechanism of absorption of light, isn't it?
Well, there's an optical back reaction. So, for instance, the cis state can also absorb
But
light.
that is very low, and it normally the transition back would be very low. I mean, minutes or hours, according to, so that it would be very depleted. But
Well, I think it depends what the frequency is. If you're right at the
you're
maximum.
excited 360
Yeah.
nanometers typically. The coming back is pushed if you are excited over 400, sort of normally. The cis back to trans.
Yes.
If you want to pump it optically, you need a higher frequency. The absorption spectrum of the cis, if I remember correctly, is very low.
Well, anyhow, leaving that aside.
In practice, your elastomer would have other chemical, I mean, the network itself would possibly absorb a little bit at around 360, and that wouldn't it limit in practice, I mean.
Yeah, there should be another absorption term here, which is independent of NT.
Yes,
It's
exactly.
a background absorption.
Exactly.
Yes.
Isn't that going to be a problem? Because if you have to go to sort of penetration depths about, say, 10 nanometers or something.
If you go to ever higher energies, for instance, towards the UV, then there's an increasing background absorption, and but
What I mean.
yeah, and I don't think one wants to operate there. I mean, one wants to operate where the solar spectrum is higher in the green.
The azobenzene does not absorb very
No,
much.
and you need dyes
You
of
need
different
different
colors.
dyes.
And in fact, you want a whole spectrum of
Can
dyes.
become more spherical.
Sorry?
There are some other dyes that maybe one could use.
Yeah, yeah.
On this point, can I ask, and this is probably very late, but please excuse me. On the first part, again, the problem of absorbing more light from the solar spectrum, say, right? Azobenzenes are fine; they absorb around that. I mean, the normal ones. But for your device, do you really need that? I mean, the changing capacitance is due to, but please correct me. I only got epsilon parallel over epsilon trace.
Yes.
But also times lambda, the deformation length, the shrinkage.
Yes.
Right? So couldn't you drive this simply by putting graphite or a nanotube, something that absorbs a lot and changes the temperature? You would go through the isotropic transition. You
Yeah,
would
yeah.
Get the lambda. You don't really need the azobenzene, do you? I mean, for the first part.
No, I mean, you could just view the azobenzene as being an alternative to carbon nanotube. It just absorbs the light.
Exactly.
And carbon nanotube would be a broader band
Or say
absorber.
graphite. I mean,
Yeah.
just carbon black. You don't really need the nanotubes, I don't think. But it would be, it's black, it absorbs very efficiently, and then it would drive your motor anyway, wouldn't it?
Yeah, I mean, you could just take a standard, make it a standard thermal engine, not an optical engine at all. So let me not insist on that.
And then it would be based on the change of, well, you still need a liquid crystal elastomer because you want to have the epsilon parallel from 16 to the trace, whatever, 7, whatever.
Yes.
And also the change in thickness, isn't it? So that
Well, that's an additional thing once you've got a solid, yes. If you had a liquid, you don't have the change
no,
of
I
thickness.
still would be exactly like this, but
Yes.
without having azobenzene added, maybe having a broad absorber. Will that still work?
It should still work. I don't think it would be as good because you want to actually have the disruption of the order both optically and thermally. Because, for instance, if it's purely a thermal engine, then you'll be limited by Carnot. Whereas if you have, well, you're always limited by Carnot, but you're, if you're having a bend, then it's subject of energy that's being delivered at 6,000 Kelvin, basically. So it's a different Carnot reservoir temperature.
Yes, in the first part, when you talk about the cycle capacitance and voltage, that you were increasing the temperature, right? And in part of the cycle. And then also at the end, in one of your last remarks, you mentioned about the effect of waste heat. So, first of all, how significant is the heat that you have to provide to increase the temperature? And is it the goal to use waste heat, or the two remarks have nothing to do?
Oh, by waste heat, I meant that if the quantum efficiency is less than 1, then when you absorb a photon, you don't produce, induce the cis state. You go back to the trance state, and all that energy just appears as heat. But that also then serves to diminish the order of the pneumatic phase in the way that Claudio was talking about.
Okay,
So the quantum efficiencies are maybe 0.8 or 50%. Yeah.
Any further question?
So I didn't talk about the mechanical turbine, and I think that's a rather different process and it's unrelated in a sense to this. Another occasion.
Well, then let us thank again Mark for